stellar constant, the idea of a stellar constant is what we want to talk about. And we'll find the stellar constant from the solar constant and the star's magnitude. We want to come up with an equation, and we also want to compare the equation we come up with one that's in the Observer's Handbook, the Canadian, the Royal Astronomical Society of Canada's Observer's Handbook. And in there, they show an equation in terms of lux. We're going to work first in watts per square meter. And this is the equation they have. They say that the illuminance of a star is equal to this expression. Here's the star's magnitude. If you work that out, you can find out what the illuminance is in units of lux. The goal here is a similar equation, but we're going to work it in terms of watts per meter squared. And what we will find, I'm using the symbol B1 here for brightness. B1 is equal to the stellar constant, and we will find it is equal to this expression here, where this is the magnitude of the star, and the units here are in watts per meter squared. And sometimes I'll use M1 for the magnitude of the star, and sometimes I'll use M superscript star for the magnitude of the star. The third thing that we will do is we will take a look at converting this 10 to the exponent e. So the basic idea is here we are, here's the sun, and 1 astronomical unit away is the Earth. And the solar constant is the power that's coming through 1 square meter. So here we are looking at the sun. We're orthogonal to the sun. We have 1 square meter orthogonal to the sun. And the amount of power coming through that square meter would be 1,360 watts per square meter. We'll look at how we get that number in a second. What we're aiming to get is a similar number for a star. So here we have a star. It's many light years away. Here we are back on Earth. We have a surface 1 meter square, orthogonal to the direction to the star, and we want to find out how many watts per meter square do we have coming on that surface. So they are the things that we're going to work out. See how we get this number by using Planck's law. So if we come over here, we have an equation for Planck's law. Planck's law is this part right here. And what we're going to do, we're going to apply Planck's law at a distance of 1 astronomical unit from the sun. So again, this is Planck's law right here. And what Planck's law tells you is if you have a body at a particular temperature, how much power will it radiate from each square meter of the surface per unit wavelength? And so if we see this quantity here is unitless. This quantity has units. So let's look at the units there. So Planck's constant is, units are joule second. The speed of light is meter per second, and we have that squared. And wavelength is in meters, and we have that to the 5th power. So if we reduce these constants, the second cancels this second, the second squared cancels this second, so we wind up with a joule per second. The meter squared up here, and the meter 5th down here gives us a meter 3 in the denominator, meter to the 3rd in the denominator. And a joule per second is a watt. So we have the meter cubed here, so it's watts per meter cubed. And what I like to do is, instead of having the wavelengths in terms of meters, I like to have it in units of nanometers. So I'm showing the wavelength in units of nanometers, so I have watts per meter squared per nanometer. So that's the units on this side, watts per meter squared per nanometer. So if we want to find the solar constant, we take the power per square meter per unit wavelength being emitted by each square meter of the sun. We find the total area of the sun's surface by using 4 pi r squared sun. And then we take all that power that's emitted and we take it all the way out to the Earth, 1 astronomical unit. And we find out then what the amount is reaching the Earth per square meter. So we do the integration to find what that total power is per square meter at the Earth's surface by looking at 1 astronomical unit away. So if we work this out, we wind up with this term here, and we still have this. And so if we put in all the numbers, we get roughly 1,360 watts per square meter as the solar constant that we see here on Earth from the sun. You can see we're doing this integration, so what we're doing is we're finding the area under the curve, and if you look roughly, say here at 0.7, and take this area and stick it over here, so now we have a rectangle with a side of 0.7 watts per meter squared per nanometer on this side, and we have 2,000 nanometers on this side for the rectangle. So again, we have this rectangle. We multiply those two together, and we get roughly 1,400 watts per meter squared, and you can see that agrees pretty well with what we actually get when we do the integration. What we want to do now is we want to look at the exact same expressions, but now we're going to put the sun at a distance of 10 parsecs. So the distance of 1 parsec is 3.262 light years, and 1 light year is 9.46 times 10 to the 5th meters. So you use the meters in over here to do this calculation. And just as before, what you can do, you can see roughly here at 0.15, if we made a rectangle here, take this piece, stick it over here to fill the area. Our integration that we're doing is finding the area under the curve, so we can use this rectangle again roughly to find that area, and we would have 0.15 times 2,000, and the units will work out fine. 2,000 nanometers times 0.15 picowatts per meter squared per nanometer, and we would find that to be roughly 300, and we actually got 320. And so the stellar constant that we want to derive, we want to find this equation yet. We haven't done that. We're going to do that next. If we take the sun's absolute magnitude at a distance of 10 parsecs and stick it in here, we hopefully will get this number. And if we do this calculation right here with m star being 4.47, we find out that B is equal to 320 picowatts per meter squared. So the stellar constant for the sun at a distance of 10 parsecs would be 320 picowatts per meter squared. To develop the equation we want to get to, let's just say a little bit about stellar magnitudes. Let's suppose we have a star of magnitude 1. It's bright. Magnitude 2 is a little fainter. Magnitude 3 is fainter yet. Magnitude 4 is fainter. And magnitude 5 is fainter. Magnitude 6 is fainter. I'm trying to show the faintness by the size of the star. Now, the rule that we're going to follow is that if the difference in magnitudes is 5, then the brightness ratio is 100. So here we have magnitude we have m sub 2 for the magnitude of this star, which is magnitude 6. Here we have m sub 1 to represent the magnitude of the star with magnitude 1. So m2 minus m1 will equal to 5. Now, a difference of magnitude of 5 means the brightness ratio is 100. So the brightness of this star is B2. The brightness of this star is B1. This is the brighter star. This is the fainter star. And the ratio is 100. Now, the thing is, how do we make 5 equal 100? We want to come up with an equation. And this is not a derivation, but it's a way to think about it. So how can we make 5 equal 100? Well, what we could do, we could say, let's take the log of this. So now we would have over here the log of B1 over B2, and that will be equal to 2. So we're closer now to 5. That's one way to look at it. So what could we next do? Well, we could say that M2 minus M1 is equal to 5/2 of the log of B1 over B2. So you see, if we do that, if we have a difference of 5 here and a factor of 100 here, take the log of that, you get 2. The 2 cancels the 2, and then we're left with 5. So we are getting somewheres by getting to that point. So what do we do next? Looking at this, what we could do is we could take the 2/5 over to this, the 5/2 over to this side, so it would be 2/5. We have 2/5 M2 minus M1 is equal to the log of B1 over B2. And what we could do now is raise both sides to the 10th power. So if we do that, then we would have 10 to the 2/5 of M2 minus M1. And on the other side, we would have B1 over B2. So we could rewrite this and say that we have B1 is equal to B2 times 10 to the 2/5 of M2 minus M1. So we'll use this to get to the equation that we want to get to. And let me just say about the magnitudes. Why is the brighter star magnitude 1 and the fainter star is a bigger number? I think one of the ways to look at this is the first star you see is the brightest one at night. Then as things get darker, you see another star, that's a second. Then there's another one, third. So I think that's the reason the magnitude is low for a bright star and large for a faint star. So now we'll see how to get the equation we want from this one. So we came up with this expression. It's not really a derivation, but it's roughly. So here's that expression again. Now what we'll do, we'll take the solar constant and we'll have that equal to B2. So we're going to put that in for B2. And for the magnitude of the sun, we'll put in its magnitude as we observe it here on Earth. And that's real bright at minus 26.83. So the B1, then if we do that substitution, here's the B2 now, 1360. Here's the 10 to the 2/5 we put in for M2. We put in the minus 26.83, and we have minus M1. We can write the 1360 as 10 to the log 1360. We have to figure out a way to get this number into the exponent. So the next step here is we have the B1 is equal to this portion right here. And now for this part here, we have 10 to the log 1360. The next step is how do we get that number into here? Well, we're going to need, there's a 2/5 out here, so we're going to need a 2/5, but there's not a 2/5 in here. So we have to multiply that by 5/2. So you see this quantity here is exactly equal to this quantity here. And so what we can do is look at what this factor right here, the 5/2 log of 1360 is equal to. And if we do that, we get 7.8338 with the 2/5 out front. So now we have the same factor out front here. We have the same factor out front here. So we can add those exponents together. So we bring this guy inside, and here it is, 2/5, all this, and it's all units of watts per meter squared. So if we add this to this negative number, we get B1 is equal to 10 to the minus 2/5 of 18.996 minus M1 watts per meter squared. So that is the equation that we were trying to get. It's the one that I showed you over here. So if we come back over here, this is the equation we wanted to get. And so we come back over here, and here it is right here. The next thing, so if we come back over here again, what we want to do is show that this expression, these two expressions are equivalent. So how are we going to do that? So if we come over here, here is the expression again that we just developed. And here is the expression in the Observer's Handbook of the Royal Astronomical Society of Canada. So we want to figure out a way to show these are equivalent, more or less equivalent. I don't know exactly what numbers they used, so we're going to be close, but it's not going to be exact. So we want to show that the B1 that we have in watts per meter squared is equal to the illuminance the Canadians have in lux. In their Observer's Handbook, they show that for the sun, 1360 watts per square meter is equal to 1.27 times 10 to the 5th lux. So we want to convert their lux to watts per meter. So now we have the same expression. We have the same term here. We have the lux, but what we're going to do now is we're going to multiply all of that by the 1360 watts per meter squared divided by the 1.27 times 10 to the 5th lux. So again, we do a similar trick on how can we get that number into this exponent. So the way to look at that is we have the 1360 over the 1.27 times 10 to the 5th. That would be equal to Here it is here, with a 2/5 and a 5/2. See, their minus 0.4 is 2/5. And let me just point out, I always like to use the 2/5 because it reminds me that a difference of magnitude 5 corresponds to a brightness ratio of 10 to the 2. So I always like to carry it as 2/5. I don't like writing it as 0.4, but it's equivalent. So we now have something that we can put inside the exponent here. And what we will do is we want to get the minus sign. We don't have the minus out here. We want to get the minus sign, so we invert the quantities in the log. So the 1360 is now in the denominator here, and the 1.27 times 10 to the 5th is in the numerator. So we need the minus 2/5, so what we can do is figure out what this is equal to, which is this ratio here. So it's equal to this if we just take the 5/2 times the log of the ratio of these two numbers. We get that. So what we can do now is put that into here. And so we're going to be adding the 4.926 to the 13.99, and we get this expression right here. So their expression in watts per meter squared is equal to this, and we can compare that with what we have in watts per meter squared. And you can see we're a little bit off here. They have 18, it works out to 18.92 here, and we had 18.996. So this is the expression we came up with. So let's compare that with some real numbers and see what we get. So if we come over here, I have two charts here. One has stars with a luminosity somewhat comparable to our sun's. And here I have stars with a luminosity much greater than our sun's. So since I used the solar constant and the magnitude of the sun that we see from the Earth, you would expect that these numbers, these stars would agree a little bit better with our equation than these, and we'll see that to be true. So I went through different catalogs, looked up stars, found out what their luminosity was relative to the sun, and found out what their distance was from the Earth, both for stars comparable luminosity to our suns and stars with much larger luminosities. And so using the R-squared loss, I figured out what the stellar brightness at the Earth would be in nanowatts per meter squared, and that's this column. And now I figured out what it was based on the magnitude listed in the catalogs. And so this is using our equation. And so here's an example with luminosity 350 times our sun. This is the nanowatts per meter squared using that luminosity and R-squared loss, R-squared. And so we have roughly 28 here and 11 here. The agreement's not too good, but down here now we have a luminosity of 18 times that of the sun. And we have 2.55 here, and we have 2.63 here. Sorry for the exponents here and a bunch of numbers over here. Of course, there's far more digits than you need there. And so down here is the comparison, again in nanowatts per meter squared from the luminosity and from our equation. And you can see the agreement is not too good. And of course, a better way to look at this is to just graph it. So what I did here, I have the brightness that we see at the Earth in nanowatts per meter squared, and what the magnitude of the star is. The line is the brightness calculated via our equation. The triangular shaped dark ones are for stars with a luminosity greater than or less than the sun's. And the square is for stellar luminosities that are much, much greater than the sun. And you can see the triangle ones fit pretty much on our curve, and the square ones don't. So this is a comparison of some actual stars with our equation, and again, for stars with a luminosity not too small or not too great compared to the sun's, we get a pretty good fit. But for stars with much greater luminosity, we don't get such a good fit. So again, in coming up with the equation, I used the solar constant and I used the magnitude of the sun that we see from Earth, that very large negative number. And so I guess you could say that it's not too surprising then that stars that have a luminosity, the triangle's a luminosity a little less than or greater than the sun's, agrees with our the expression, but stars that have a luminosity much greater than the sun's do not. And so if we go back over here, so the agreement's pretty good. So if we go back over here, we've done everything that we want to do, except we want to rewrite this equation, and instead of having 10 here, we want to do it with the exponent e. So here's the expression we came up with in watts per meter squared. Now we want to rewrite that expression, and instead of having 10, we'll use the exponent e. And why would we do that? Well, we'll see. So the first step we'll take is we'll calculate the value of 10 to the minus 2/5, 18.996. And if we do that, we get this number here. Now that's in watts per meter squared, and we still have the 10 to the minus 2/5 m star. So there's that term. Now what we'll do is we'll convert the watts to nanowatts. So this number then becomes 25.21 times 10 to the 2/5 m star. And I just want to say again, I always like, instead of having minus 0.4, the way the Canadians did it, I like having the 2/5 because the 5 tells me a difference of 5, and the 2 tells me that the ratio of brightness of stars with a difference of magnitude of 5 is 10 to the 2. So I always like having 2 and 5. All right. So how do we convert this to exponent e? Well, you can recall that e to the power of a is equal to 10 to the power of b. Now, what kind of relationship can we come up between those two? Well, if we take the natural log of both sides, we'll have the natural log of e to the a is equal to the natural log of 10 to the b. And so this term will reduce to a. This term will reduce to b times the natural log of 10. So here we have our expression again, and we now write this as e minus the exponent we have, and now we have to multiply that by the natural log of 10. So the b is this quantity here, and then we have the natural log of 10. So if we calculate this out, it works out to e to the minus 0.921 times m star. And again, that's in nanowatts per meter squared. So the stellar constant, the exact equivalent to this equation is this equation. But you can see this is almost 25 here, and this is almost 1 here. So we can come up with a stellar constant approximate, and that would be 25 times e to the minus m star. I'm not suggesting that there's anything physically significant about the E, but it is kind of interesting that this approximately works out to a very clean expression. So how does this approximation compare with this exact or this exact? So if we come over here, so here's our exact expression the way we originally wrote it with 10, and this should be a superscript M. It's a superscript star on the M. So the exact equivalent to this is this. So I have plotted our equation here. Now I take the approximate equation and I've plotted it here. And you can see the agreement isn't, well, it's pretty good up here for a few magnitudes, but when you get down further to fainter stars, it's not too good. But it's still an interesting expression. And so I thought the equation ought to have a name. I'm not a pompous guy, so I didn't name it after myself. It turns out our first grandchild, a little girl, was named Macy. She's the daughter of our son Wyatt and his wife Christine. And our first grandson, his name is Evan, and he's the son of our daughter Andrea and her husband Tyler. So I want to call this expression here the Macy-Evan equation. So people have emailed me over the years asking questions about some of the things that I show and making some comments, all of which I appreciate. But there seem to be two common themes that people would sort of ask as sidebars. The first one was, or the more common one was, they wanted to know who were some of the famous scientists that I met. I actually met a couple Nobel Prize winners, but one of the more interesting persons that I met was Clyde Tombaugh. Clyde Tombaugh was the discoverer of the planet Pluto. Another very interesting person that I met was Carl Sagan. Everybody knows Carl Sagan with his Cosmos series. But what has always amazed me with the science were the regular folks who have come to me and asked me some very interesting questions. And a few years ago when we had the transit of Mercury, Christine Anthony, who was a scientist meteorologist at WFMZ Channel 69 in Allentown, she wanted me to talk to her about the transit of Mercury. So we met up at Lake Towey in Bucks County, and I had my telescope set up there, and I just want to show you a picture now of the cameraman, Adam Klein, and following that picture of Adam Klein and myself, you'll see a picture of me and Christine Anthony. Another very interesting person during the transit time, I went down to Belmar, New Jersey to observe the transit, and a lady and her husband had stopped by a couple times while I was watching the transit right near the boardwalk. There's a video on that. And she later came back. She also asked very good questions and all. And she later came back and she treated me. She saw me sitting there all day, so she treated me to some Dunkin' Donuts. With the comet of last year, today is August 20th, 2021 with the comet of last year, channel 69 WFMZ asked me about the comet. So in that case, we had a camera lady named Jenny, and the reporter was Holly Harrer. And next is a picture of Jenny and Holly Harrer. Jenny's the one with the camera. But of all the people that I've come across in the area of science, the most amazing one to me was my thesis advisor. His name is Harold Story at the State University of New York at Albany. And so in the picture that follows, what you'll do is you'll see Harold Story. He's standing in the middle, and I'm off to the right side in the picture. And the person next to Harold on the left side of the picture is Marvin Pryor. And what's really interesting about that is Marvin Pryor was Harold Story's thesis advisor, and Harold Story was my thesis advisor. So I always like to say that Marvin Pryor is my grand thesis advisor. So the second sidebar question that people often ask me, they said, where am I? Where is this place? Where am I? They wanted to know if I was at some university borrowing whiteboards or something like that. And that's not where I am. And where I am is a secret. So I have a few more videos that I'd like to do in the future. With things changing, I'm not so sure I'll be able to get to them. So this may be the last transmission from this location, the secret location.